Hey everybody, Brian Forget here. Welcome back. So this is going to kick off our sort of introduction into things in the networking space, and with that in mind, today, OSI model. What the heck is it, and why is it useful? So big picture. To my mind, OSI model is useful in two basic ways. One, you work for a company that's making stuff, right? Whatever that stuff is, you want to be able to make a network cable. Or heck, I got one lying around here. You want to be able to make a network cable and not have to worry about, is it going to support IPv4, IPv6, whatever. You just want to stay in your lane and make your thing. Or a network card, right? Hang on, yeah, here we go. Some gadget with a network port on there, right? You want to be able to stay in your lane, make your thing, focus on what you want to focus on, and let others focus on their piece of it, right? And so from that perspective, the OSI model is about creating standards that define the way in which you need to make that cable, that port, that IP packet, right? If you get into routing or something else, that TCP, UDP, whatever down the way, and you can standardize, here is how I'm going to deal with the thing I care about, and here is what I'm going to expect to be handed from other layers and hand to other layers. Okay, so that's the first piece of it. You work for some company making something. That's part of the OSI model. The other piece of it is troubleshooting, right? You've got this network equipment that's in your rack and something's not working right. Depending on the symptoms that you've got, that's going to point you to basically focus then on one piece or another of equipment sort of and where it fits into that OSI model as well. All right, so two sides to it, making stuff, troubleshooting stuff. Let's get into it, and boop. I'm tiny, hello. Okay, and when in doubt, draw stuff, diagram. All right, I'm in Paint, why not? But let's just nail it down first. OSI model is not the only model for sure, but the main one I tend to think of. And whatever mnemonic you've already got in your head, cool, that's the right one. But for me, it's always been, please do not throw, I can't type, that's fine, sausage pizza away, yeah. All right, how is that useful? What the heck is going on there? Okay, well, the layers, right? Physical, data link, network, transport, session, presentation, and application. Let's nail those down. I usually do it in kind of reverse order there, but yeah. Physical, data link, what do we say? Network, session, oh my goodness, transport. There we go. Presentation and application. All right, and these are our layers 1 through 7. In this case, bottom up. I like that. So, right, going from that perspective of what do these represent? Well, physical, start at the bottom for the moment. This would literally be something like cable. Or also the speed, the standard associated with it, right? So the cable or the port, right, if it's an RJ45 plug right on here, or the associated port on the NIC, well, it's going to need to be a certain number of millimeters wide, right? The placement of the pins in there, the 8 wires and the associated pins are all going to need to be the exact right space. The angle of the little clip on there, right? This is all part of the physical standard, in addition to, it's just for RJ45, right? But the cable itself, in addition to how many twists per meter are in there. Is it solid or is it twisted? Little bits of copper. Both are acceptable depending on what you're doing. Is there shielding in there? Is there separation between those wires? And those are going to be the differences between a Cat, back in the day, Cat 3 to Cat 5, 4 to 8. wires in there. The amount of shielding, twist per meter, separation, those are the subtle differences between 5E, 6, 7, 8, the extra like grounding even a little bit when you get into 8, that allow for the transmission on there. The speed as well though, the pulses of electricity that that's going down the wire that allow for 100 meg, gig, 10 gig, 25, whatever down the way. That's part of that physical layer as well. So physical layer again would be defining the basically medium and the basic formatting for signaling. Okay, data link. The data link layer is where we're talking about our low-level addressing and the basic rules about when and how you talk. Not the pulses of electricity exactly, but like the spacing between, the formatting of the actual ones and zeros that you're going to be sending based on that 1 gig or 10 gig or anything. But that low-level addressing and the sort of rules of the road for basic communication. Right, so this is, for instance, where Ethernet lives. Ethernet is a layer 2 network technology that has its low-level addressing, MAC addresses, and basic rules, CDMA, that allow for your low-level format of the transmission. Yeah, right. Okay, network. This can feel a little confusing because we just talked about addressing and basic rules for communication, and network kind of does that too, but network allows for communication between different networks. Yeah. All right. And your examples here might be like IPv4, IPv6. All right, whatever you come up with next week, I don't know. As long as you can convince enough people to do it as well. Oh, come on, hands, there you go. And so this is our network layer. Here, we'd be, like we said, talking about that IPv4, IPv6 as opposed to Ethernet at layer 2. For hardware, by the way, at layer 2, we'd be talking about a switch, a classic layer 2 switch. Would be a layer 2. And a router is what we'd be talking about at layer 3. Yeah, and if it supports IPv4, IPv6, whatever you come up with next week, right, that's what it's going to focus on, and that'd be layer 3 functionality there. Layer 4, transport layer. This is the first time we're getting into actual user data. I've got some file and I'm sending it somewhere. Well, an individual Ethernet frame is by default about 1,500 bytes maximum, but probably whatever file you're sending is way bigger than 1,500 bytes, and so it's got to be split up. If you are using TCP, Transmission Control Protocol, UDP, User Datagram Protocol, technically even ICP, but you wouldn't use it for message sending exactly like that. But TCP or UDP or whatever else you come up with next week is going to take that 100 megabyte file, gigabyte file or whatever, and split that thing up into chunks that then fit inside of the TCP part of the message segment, or UDP datagram, that fit inside of the packet, inside of the frame that gets turned into pulses of light or whatever. So our transport layer, that is our basically splitting up our files into chunks, and it's also potentially the control to make sure that whatever is sent is received, certainly on the TCP side. UDP doesn't have that native to it, but maybe something else sitting inside of there might be taking care of that. But yeah, transport layer, layer 4. Here we go, message handling. And like we said, this is where you're going to be splitting up whatever file, whatever data to be sent into chunks that fit into your messages. Yeah, and maybe ensure that things get there. Depends, right? TCP, that's its job. UDP, doesn't worry about that. Something else inside of it can handle it if you want to, like quick. Okay, but yeah, TCP, UDP. And technically, also here you could argue ICMP, but you could argue ICMP exists in a lot of places. I'll just leave it little for space. Okay, let's move stuff down. Session. The session layer is one conversation. And so this layer 5 here is where your firewall kind of lives. There's, layer 7 firewalls too, but basically, at least historically, session is where the firewall lives. But this is, like we said, a conversation. And if it's TCP, then that would be the pairing of the same source and destination TCP ports and IP addresses that is me going to this, HTTPS session that I have to your web server. If it's UDP, then maybe it's this file that's being sent through TFTP, or a voice over IP call that's being sent out through RTP that's sent along the way, again with a pairing in that case of UDP ports, source and destination, and IP addresses as well. But yeah, so that's a conversation, and that's going to be a this is the first one that isn't actually like in a message sent, generally speaking. It's that some firewall essentially is going to be keeping track of it, whether that's software on your computer or an actual appliance on the network. But usually anyway, pairing of TCP or UDP ports and IP addresses, or I'll say network addresses. And it represents one, generally speaking, this is a bit of a broad term here, but one conversation, one file being sent, or set of files being sent, or something like that. And the firewall again lives here. Right. And like we said, generally there's not necessarily like a marking within the frame packet segment, right, that says this is a session, other than those pairings of TCP ports and IP addresses, or UDP ports and IP addresses. Yeah. All right, so your computers, your firewalls are keeping track of this. Presentation layer, layer 6. This one is one of those funky ones that very often is like, the presentation layer takes things from the session layer and hands it up to the application, and from application down to session. Nothing has to happen at the presentation layer, right? It is true that it passes between layer 7 and layer 5, but very likely at presentation layer, this is being used for compatibility or for encryption. So it kind of depends. Okay, so what the heck is up with that? Well, if I'm sending a message from my computer to yours, and I type it out in ASCII, and I send it over to your computer, it might be that your computer is not expecting ASCII as its default language because maybe you live in a different country. Well, ASCII is a format for handling characters that is purely based on sort of American English. It can be broader, but yeah, so that's the original intent. But Unicode is a mechanism for taking characters, all those same American English ones, but also just about every other language, and like most every emoji that you know of at this point as well, are all Unicode characters. And there, when Unicode was first built out, it basically said, cool, for any of that stuff that was already in ASCII, great. There's basically a padding that sits on the front of that, and then that says, hey, this is what we're using for any of the American English characters, and then just the same ending. And so it's easy to convert that if I send an ASCII A to your computer, but your computer is looking for Unicode instead, that it can be converted over to Unicode before it gets sent to you. Or that whatever application I'm using can convert it from ASCII over to Unicode before it gets sent to you, more to the point. And so that might happen at the presentation layer, right? ASCII to Unicode. Yeah. Or depending on what you're doing, maybe encryption happens here. maybe whatever chat protocol we're using, old school AOL Instant Messenger, but hey, somehow encrypted, ICQ or something, right? On my computer, when I go to send that, well, yeah, I typed the letter A and pressed enter, right? And when it was sending it off to do, I did the whole Unicode thing. But maybe it's also going to be encrypting within that application before it sends it on down the way, instead of relying on like HTTPS as a separate thing. Yeah. So again, compatibility, or maybe encryption, like we said, maybe ASCII to Unicode, but or maybe nothing happens here. It's a model more than it is a set of rules, this OSI thing. All right, presentation layer. And then our application layer. The application we're talking about here is not Word, it's docx, right? It's not Chrome, it's HTML. And this is our basic formatting of data that whatever application you're actually using is going to expect, right? So not Paint, but JPEG. Like we said, HTML, not Chrome, right? JPEG, not Paint, right? Or whatever, makes sense. Okay, and so this is our OSI model. And let's go actually make some sense of all this then. And can I make things even bigger? Yeah, we'll just work over here for a second. Let's imagine we've got a couple of computers. There's, get one. Hey, there we go, 1980s looking computer. It was so beautiful. Let's make another. And put it over here. And let's say I have got up, Teams or whatever chat protocol we're using, and I literally send you the message, hello. Boop. And I want to send that to you. Okay, well, I typed that in, I pressed enter, and inside of my computer, we're going to go through basically this whole OSI model, right? The computer itself is going to take that message and it's going to say, well, what's my basic formatting for this message? Let's stick with my imagining from a second ago. I'm not saying this is exactly how it works on some application or another, but let's say that I typed it in and it was in ASCII. And it takes that hello, and up here, application layer, right? Then maybe it's going to be formatted again in ASCII. And then at presentation layer, it says, oh, well, I'm sending it to so-and-so's computer, your computer. But your computer maybe, is expecting maybe Unicode, so maybe it does that conversion from ASCII to Unicode. Okay, sure. We just basically took, and now it's going to take up more bytes of data for the same thing, because literally each character is going to take up more space in Unicode instead. That's fine. Okay, and then still inside of my computer, the session layer 5, my computer is going to say, oh, Brian is sending that message to you, I don't know, Jorge, right? Whatever your name is, right? And so do we already have a session open for that? If not, then maybe let's go make an entry in our firewall to see if a communication is allowed and start that up. At layer 4, this is where we're actually going to start to do something with the data, like we said, take this file, this whatever data, and chunk it into something that's going to be able to be sent out. And now we're going to say, okay, what protocol am I using? What layer 4 protocol am I using? Is it TCP? Probably. Is it UDP? Probably not, but maybe. Okay, and so now it's going to say, okay, well, how big is this thing? Does it fit inside a normal standard message? I think our hello will. And so it's going to take that, and it's going to make it the payload of some TCP message. And that TCP message that this hello is the payload of is going to have its own little header with, you there, for the TCP header, with a source and destination port, right? And so the destination port, let's start with that actually, destination port is going to be application specific, right? So whatever application, FTP, HTTP, whatever, have these sort of standard TCP or UDP ports. Let's just imagine this rides over the back of HTTPS, and so maybe destination port is 443 that it's sending out on. The source port, ooh, what do we do with that? Well, there's, for TCP, 2 ports always, like we said, a source and a destination. Destination, when you're sending out, is generally, if you're starting the conversation, is application specific. I send it to whatever you're going to be listening in on this TCP port that your application's looking for messages coming in on. The source is going to be a random high number one, generally speaking. Most operating systems, that's TCP or UDP ports above 50,000. The different apps, different operating systems can do something different. It's 1 to 65,535, I think. So let's say our source port that my computer randomly picks is 50,002. Sure, why not? Okay, and there'd be a little more going on in the TCP header as well, but that's the part I'm going to write anyway, for my TCP here. Okay, and then that was my, coming on over, that was my layer 4. Layer 3, network layer. Okay, well, it's sending from my computer to yours. It doesn't necessarily know your name or anything like that as far as the messages it sends out on the wire, right? But it's going to need to know an IP address. And so let's assume that my computer here already has an IP address. Otherwise, I'm going to be in trouble. And my IP address is, let's pretend silly stuff. Let's pretend we both have public IPv4 addresses, and I'll say so we can skip NAT and all that. I'll say I'm 1.1.1.1. I love it. Definitely not, but let's pretend that's right. And let's say your computer has the IP address, definitely wrong, but it's 1.1.1.2. Sure, why not? Okay, so at the IP layer, it would take this TCP message, TCP segment, and get rid of this extra little bit of lines here, and it would wrap that up, still inside of my computer, inside of, in this case, we're imagining IPv4. And there's more in the IPv4 header than just destination and source address, but for our purposes at the moment, let's just say that the IP header has, like we said before, a source and a destination address. And apparently my source here is, go back to my red, 1.1.1.1, and my destination apparently in this imagining is 1.1. Go back to red, be similar. There we go. 1.1.1.2. Okay, great. And so here, again, there'd be a little more on that, but still, here would be my packet header that is stuck on the front of TCP, still inside my computer when this happens. Okay, and now still inside my computer, if I want to send you this hello, well, I got to send it not just in TCP, not just in IPv4, v6 or whatever, but if this is an Ethernet message, well, yeah, I'm going to send it out in Ethernet. If it's Wi-Fi, it's going to be Wi-Fi. That's a different layer too, right? And so we're going to need MAC addresses here as well. And for our silly example here, let us also assume that these are both on the same network, even though I gave them these public addresses. They're right next to each other, why not? Let's say that my computer has a MAC address of A. Okay, now MAC addresses are 48 bits, hexadecimal characters. It's definitely not just a single character. But I don't want to write that, and I don't think you want to read it, so let's both just agree to lie and say my MAC address is A. And let's just imagine, in the same kind of lying, that your MAC address is B. Sure, I love it. So over at the Ethernet header, in this case, the source address and destination address are going to be written in there. And it looks like in this imagining, like we said, our source address is A, and our destination address is B. And again, there's more than that than there would be in the header. That's all I'm going to put in here for the purposes at the moment. And the whole thing gets wrapped up. And this would actually, there'd be not just a header, but a footer, a tail as well for Ethernet. Okay, and when we talk about an Ethernet message being by default a maximum of 1,500 bytes, that is the 1,500 bytes, that whole thing. Ethernet message with an IPv4, v6 or whatever inside of it, with TCP or UDP or whatever inside of it, with an actual payload. Yeah. Okay, and at that point, this whole thing was all happening inside my computer. And now, that gets sent out of my NIC, out on the wire. I'm going to need a wire here. Maybe there's a switch between, maybe there's something else. Let's just go super simple and pretend that there's, that's funny, that there's literally just a cable plugging these two computers in for extra simplicity right now. Okay, and now we're down to layer 1 for sending it out there, right? And now it's pulses of electricity sending out on the appropriate 4 wires of this cable. Or if it was Wi-Fi instead, it's radio frequency and very similar, but amplitude of RF, a different part of the electromagnetic spectrum being sent out. Whatever else, Apple Talk or something else back in the day, it would be different. But in this case, it's pulses of electricity being sent out at gig or whatever on these things as the signal being sent across this media. Okay, and that message is what gets sent across to your computer. And your computer is going to basically walk back up the OSI model. It got that message from you, and it says, well, first off, does my NIC support whatever that was? Does it know how to meh back into ones and zeros? And so, yeah, let's assume so. And we got our layer 1 taken care of, right? Layer 2, it's going to say, okay, well, there's this message that came in to my MAC address, destined to MAC B, am I MAC B? If not, it would just throw it away. But no, it is. So it looks inside. Looks in there. Boop. And it says, okay, it's to this IP address 1112. Is that me? Yeah, it is. So it looks inside. And it's from TCP port 50,002 to destination TCP port 443. Am I accepting messages for that, right? Like, is my firewall set up to allow incoming messages on this application, basically? If not, throw it away, right? If so, cool. Let's keep looking. And if there's already some session associated with that, layer 5, then okay, it's part of that session that's already allowed or not. If not, within the internal software firewall, set it up. Also, the application is going to be associated with whatever particular port. In this case, we're imagining 443. Maybe a little more likely it's some, 8,279 or something. I don't know what that's for, but but this is why you have different application-specific ports so that your computer knows which app to hand that back up to. Okay, but at that point, right, it's checked, is this allowed? Is it going to the right app or whatever? Right now it gets to your app, and it's going to say, oh, here's, this Unicode data that passed your app, and it shows up on your screen. Yes! Okay, and this is what we're talking about with the OSI model, basically. You send data, and inside of your computer, it is going to wrap all that stuff up, part by part, bit by bit, so it can send it out on the wire. And the wire doesn't have to know what Unicode is. The wire doesn't have to know what TCP or UDP is. It's just following the standards. Your application doesn't have to know how wires work and doesn't have to care if it's Wi-Fi or Ethernet or something you come up with next month. It's just focused on the piece it cares about. Yeah. And so again, from the perspective of building things out, individual application makers, operating system makers, NIC makers, cable makers can focus on the piece they want and expect that others will handle their part. From the troubleshooting perspective, you could look at this and say, well, hey, I can't send messages in this chat program from my computer to yours, but I can ping you. Oh, well, if I can ping, but I can't send these messages, well, it's not a layer 1 problem, right? The cable's fine. The NIC is fine if I can ping, almost certainly anyway, but not send messages. Instead, the difference there is going to be more of a layer 4 and above problem, right? Ping is ICMP, and this other program might be using TCP or UDP, might have an ACL somewhere between here and there blocking it, might have software firewall on these computers blocking it. If you're doing a modern wireless deployment, it is very likely that there is basically a built-in firewall on those wireless controllers or access points as well that might be blocking it as well. Right? And so by being able to say this piece is working but not that piece, that can point you to the right thing for troubleshooting. One application is working but not another. It's layer 4 and maybe above that you're focused on, but you're not so much worried about routing between here and there, if some things are working but not others, about layer 2, about layer 1, right? Switching basic cables, if some things are working but not others. If one whole section of a building can't talk at all, or can only talk amongst themselves but not somewhere else, oh, well, that sounds more like a routing problem, a layer 3 problem. Y'all can all talk to each other no matter what, but not elsewhere. Okay, well, different networks aren't able to talk to each other. That whole section over there can ping, can get DNS, can check their email, but can't do this one application. Well, well, probably not routing. We're probably back up to saying some firewall between here and there is blocking things, or ACL. All right. So what do we talk about today? Let's sum it up. OSI model, like we said, is good for two things to my mind: building stuff and troubleshooting. Either way, for building, it's about being able to stay in your lane and focus on that. For troubleshooting, it's trying to figure out which of these lanes is the problem. And then that points you for which equipment to start looking at, or which configuration on the equipment between the source and destination to start looking at. Thanks, everybody. This has been a blast. Hope you're having fun. We'll see you next time.